Hi everyone, today we are talking about our final presentation. Our system is Energy Efficiency Optimization of Building Room Design. We include wall insulation, geometry, and temperature control. Our system aims to minimize power consumption in a single room while still maintaining thermal comfort. By doing this, we can improve energy efficiency of the room and still feel comfortable. The optimization is limited to within the room, and we focus on three key factors, including wall insulation with effective rate of heat loss, room geometry which lead to the comfortable environment, and the last one is heating system design which impact the heat generation efficiency.
Okay, now let's review briefly about subsystem 1. In this subsystem, what is changed is that now we are trying to minimize the heat loss by selecting the most optimal insulation materials and also the thickness of all layers. Therefore, instead of having two design variables, now we have five design variables. And moreover, we are also adding the more detailed cost and also the strength as a constraint. And for the optimization method itself, since subsystem 1 involves both continuous and discrete variables to select the thickness of each layer and the materials respectively, one of the appropriate algorithm is genetic algorithm. And after that, we run it 5 times and choose the smallest one. And these are all the new parameters and constraints which include the total thickness, total cost, specification, and also the structural properties.
Subsystem 3 has been adjusted based on comments from the interim report as well as advice from Professor Saito. We now use a surrogate model based on the CFD results. We employed a polynomial regression from the 11 data points we obtained from OpenFOAM. We have preferred a larger sample size but we are limited by time. To maintain a higher degree of freedom, we determined that a linear fit will be sufficient given its high R-squared and adjusted R-squared value. And this is the surrogate model. On the right, we see what X and Y represents, and these are the constraints.
For our subsystem 3, we will optimize the heating system. Our goal is to minimize the total energy consumption rate of the system while also maintaining thermal comfort of the room. To achieve this, we optimize three design variables including airflow ratio, supply mat flow rate, supply temperature. We also apply constraints to ensure the thermal comfort and set aside constraints for each design variables. We optimize using F-min-con.
The overall subsystem can be described in the perspective of system flow diagram in the idea formulation as follows. Each subsystem has their own design variables shown here in a navy colored arrow. Subsystem 1 solves minimum rate of wall heat loss independently, which will be the shared variable for subsystem 2 and 3. Without the idea formulation, subsystem 2 and 3 interacts in a way where subsystem 2 solves the room geometry X and Y to minimize thermal comfort PMV. Then it is translated as area for input of subsystem 3, which then solves the heater inlet temperature T supply and airflow speed U supply that minimizes the total energy, where the T supply and U supply is also feedback again back to the subsystem 2. The idea formulation in this case enables us to decouple these coupling interactions between subsystem 2 and 3, and hence auxiliary variables are introduced here, which are T supply tilde, U supply tilde for subsystem 2, and X tilde and Y tilde for subsystem 3.
Now let's talk about the optimization model for the objective function. As mentioned earlier, that the subsystem 1 is independent and the optimal solution serve as the intermediate outputs or become an input for the subsystem 2 and 3. And this is how all the three subsystems are all integrated into the full system model. And although subsystem 1 does not explicitly appear in the system level objective function, its influence is embedded through its impact on both thermal comfort and also the energy consumption, which are evaluated in subsystem 2 and 3. And the system level objective function is formulated as the weighted summation of the subsystem 2 and subsystem 3, which combine thermal comfort and also the energy performance. And the weighting values are set equally as we consider that both comfort and the energy used are considered equally important in the design process. And therefore, here the design variables of the system level optimization still include the design variable from subsystem 1 and compile it together with the subsystem level. And for the design variable classification itself, the function type of our system is nonlinear, with a variable type of mixed integer as the material selection or x1 is defined in the integer form while the rest is in continuous form. And these are the system level constraints which combine all the subsystem constraints. And for subsystem 1, we also have the side constraint for the materials index and the thicknesses. And these are all our parameters for the system level optimizations. And for the trade-off, lowering the supply air temperature indeed reduces the energy consumption, which benefit the energy objective. However, if the temperature drops too low, it might fall outside the range of the thermal comfort, which make the occupants feel uncomfortable. And to compensate this, better insulation or increased air velocity can help maintain comfort, but then higher air velocity also increase energy use, which create a new trade-off. And better wall insulation will definitely reduce heat loss energy demand, but it often comes with a higher material cost and might reduce the structural strength. And it create a new trade-off between the energy efficiency, cost, and structural performance. And higher air velocity indeed improves thermal comfort, but it also increases the energy demand. And on the other hand, lower air velocity saves energy, but it might not maintain the required comfort level.
These two diagrams show the difference between subsystem and system optimization. On the left side, we we can see how each subsystem is optimized individually, and on the right side, we can see the system level optimization that show the linking variables that pass data between subsystems, such as QO from the subsystem 1 to subsystem 2, and both QO and RO from subsystem 1 to subsystem 3. We also have share variable used globally between subsystem 1 and subsystem 3 for temperature condition, and subsystem 2 and subsystem 3 for room dimensions. We made the assumption to simplify the system. Firstly, we assume a constant outdoor temperature. The thermal conduction is occurred to the wall only. The transient behavior is not included. We apply Fourier law under an assumption of one-dimensional conduction. In our circuit modeling, we assume that the input and output data exhibit linear behavior. That in hypercube sampling is sufficient on data input for circuit modeling. Finally, we assume the wall insulation is independent of both room geometry and heating system. Now, for our modeling step, we begin by guessing the values for heating input for subsystem 2 and also guessing the room dimension needed for subsystem 3. Then we use select variables and output from subsystem 1 to obtain the correct value for each subsystem. Next, the system objective is evaluated using the corrected input from subsystem 2 and dimension from subsystem 3. Finally, the select variables are updated through equality constraint.
Moving on to the optimization method. Since subsystem 1 solves the objective function of wall heat loss independently, we employ genetic algorithm using MATLAB's built-in function due to the nature of the subsystem 1, which involves solving the optimal of mixed integer variables. The result of subsystem 1 is then used for subsystem 2 and 3, which is combined as one system using the idea formulation. The system level optimization in this case is done using MATLAB's built-in function fmincon due to the multivariable functions with nonlinear constraint in the system itself. Recall again the interactions between subsystem 2 and 3 in the figure here as one system, which is the idea formulation. The update between the auxiliary variable and the output can be done using fmincon, which iteratively update the guess variable with the output variable at each iteration until the objective function is reached. The optimization result of subsystem 1 is shown at the top 3 of the table. Here we conducted 5 trials for the GA optimization, which result in 5 optimum variables and the objective function, which is the wall heat loss. Within the trials, the change of the optimum variables and the objective function are insignificant, so we only show the minimum value here, which is the 4th trial. The system level optimization was run using 5 different initializations randomly, which consistently yield to the same result. The result of the system level model suggests a room dimension of x and y of 0.5 and 4 with corresponding image in the right side. The usage of heater with temperature 30 degrees Celsius and airflow speed of about 1 meter per second is optimum for the corresponding room dimension. The objective function f can be decomposed into the absolute value of the spatial average PMV of 0.5 and the energy consumption of about 9.15 kilowatt.
Now that we have obtained our optimization results, we conducted a series of sensitivity analysis on both active constraints and selected parameters. The original F star value is shown for reference. The 3 constraints chosen are the cost per unit area for wall insulation, the area buffer pertaining to subsystem 2, and the supply temperature that affects all 3 subsystems. We adjusted the cost per unit area from $40 to $36 and $44. We adjusted the area buffer from 10% to 5 and 15%. So in this case, the perturbation is much larger than the typical alpha of 10% because the value itself is a very small percentage already. Lastly, we adjusted the supply temperature from 30 to 27 and 33 degrees Celsius. The table below shows the net difference in objective function, the constraint sensitivity coefficient, and its ranking. Next, for the parameter, we decided to adjust the outdoor temperature, the room maximum width, and the heater's efficiency. The outdoor temperature is perturbed from 0 degree to -3 and 3 degrees Celsius. The room width was adjusted from 8 meters to 7.2 and 8.8 meters. And the heater efficiency varied from 90% to 81 and 99%. The table below shows the net difference in objective function, the parameter sensitivity coefficient, and its ranking. Let's now discuss the results of the sensitivity analysis. We assess each item based on whether the constraint was truly active, whether the result makes sense, and whether it can be acted upon. For the first constraint, the objective function increases when the constraint decreases. This is expected because a cheaper material will have poorer insulation capability, and this constraint can be easily acted upon through increasing its wall budget, but due to its low sensitivity, it may not be a worthwhile investment. For the area buffer, the objective function increases when the buffer decreases. This is expected since the constraint acts on the lower bound, which means that a smaller buffer means a higher minimum floor area, and so more energy is required. This is typically not actionable since space allocation is often fixed in floor plans. For the last constraint, it's intuitive that more energy is required to sustain a higher supplied temperature. Let's now look at the parameters. A lower outdoor temperature results in a higher objective function. This is consistent with the heaters here in Ann Arbor that probably have to work harder in winter than in spring. However, since we can't change the weather, this cannot be acted upon. Next, increasing the room width requires more energy due to the larger surface area that allows heat loss. It is similarly hard to implement due to allocated floor plans. Finally, the heater efficiency has a higher sensitivity. because high efficiency requires less input power for the same output. This is effective, probably actionable, but this is not scalable, because there's always an upper bound as to how efficient a system can be.
As my friend mentioned earlier, we can clearly see the difference between system level optimization and optimizing each subsystem individually. Interestingly, subsystem 1, wall insulation, gives the same result whether optimizing on its own or as a part of the whole system. This is because it depends on mostly isolated parameters, and its output like wall resistance and heat loss is used as input for other systems. However, subsystem 2 and 3 show noticeable change when optimized the whole system. They share linking variables like room area, supply air temperature, and air velocity, which introduce trade-off between energy use and thermal comfort. So optimizing the entire system together helps us manage those trade-offs better and result in a more energy efficient and balanced design. From an engineering perspective, our system aligns with the logic, so minimizing energy consumption requires minimizing supply temperature that maintain thermal comfort, but also need to minimize heat loss through the wall as well. Minimizing heat loss is challenging, but the system finds a wall component that maintain the strength to withstand construction force and also the cost and thermal property of the insulation as well. Considering thermal comfort or PMV, our system always tries to balance this factor and also energy as mentioned in the sensitive analysis. The result of system indicate that energy used purely for the subsystem 3, which involve minimizing heat loss through the wall of the system 1, may not be sufficient enough to fulfill the room thermal comfort requirements. While our current model uses equal objective function, there is room to make it more flexible and realistic. So first, we can use unequal weighted objective function to reflect the different design priorities. Next, we can explore more flexible room shape to see how they affect the temperature distribution which lead to the PMV. And then adding more data points to improve the accuracy of the model for the room shape design. And then modeling how the system responds over the time to the temperature change is also help to understand energy use to the system as well. And next, we can include more control parameters to meet energy efficient standard like LEED certification. And at the end, even this area for improvement, our current optimization is solid enough to give us variable insight to how different desirable interact and how they impact both energy use and thermal comfort.